Now we're going to look at how to construct a queue. Just like with stacks, a queue is a data structure that we could create using either an array or a linked list. I'm going to use a linked list so we can gain more experience. But first, let's talk about what is a queue. So a queue follows the first in, first out model. You've been in many queues in your life because a waiting line is a queue. So imagine we have this here. Here's the entrance. Here's the exit. And so what happens? Person comes in here, and person 1 is here, and then they're followed by person 2, followed by person 3. And then who leaves first? Well, person 1. And then they're followed by person 2, and then followed by person 3. So that's why it's first in, first out. All right? In terms of linked list, we're going to use a singly linked list, so we'll still have a head that points to our first node. We'll call it node A. This is node B. This is node C. This is last address here is null. But unlike in our stack, we'll keep track of the last node as well, and I'm going to call that tail. So head is where we enter the chain of nodes, and tail should be the last one. So which in is the one that we add to and which is removed from? Because that's what this means. First in, first out means that when we add a new node, it goes on either end. But when we remove a node, it comes from the opposite end. Now from a theoretical perspective, we could use either end for either part, as long as they're on opposite ends. But from a practical perspective, that is in terms of writing the code, turns out they're not necessarily the same. So let's look at what would happen to add to the head end. So if I add a node here, right, this would be just like what we did with my stack model. Temp would equal malloc. To get some space, we would store our data. I would say temp next equals head. Right, that's what ties this together. And now that I've safely stored the address of node A in the temp node, now I can say head equals temp. Well, if we add to this end, so here's where I'm going to think the node will be. Once again, I have temp malloc, or temp equals malloc. I'm going to store my data. Now I need to set the next here to null. So temp next is equal to null. And then what's left to be done? Well, it turns out two things. I need to have node C connect to the brand new node, and I need to have tail point to the new last node. But if I say tail equals temp first, I no longer know where the last node is at, short of coming back in at the head and working my way back down. So instead, what I want to do is this. I want to say tail next, which is this node, is equal to temp. That's how now it's connected like this. And now I can safely say tail equals temp. So at least for the way I wrote the two processes down, this appeared to be 4 lines of code. This is 5 lines of code. It's not that big a difference between the two. I'd be okay with either one. Let's see what it takes to remove a node from one of the ends. All right. So let's create my linked list again. All right. If I remove from this end, which means to remove A, it's going to be like in my stack model. So if I say free head, that will free up the memory for A, which I need to do. But now how do I know where B is at? Because ultimately I need to say head now points at B to make that the new first node. So instead what I do is this. I say temp is equal to head next. Because next, the next component of the A node, which head points at, contains the address of B. So head next. And now I can say free head. and then head equals temp. So free head frees up this block of memory. Now I say head is equal to temp, which is pointing at this right here. What if I remove from this end? Well, certainly at some point I need to say free tail. Well, what else needs to happen? Well, I need to say that tail points at B now, and also B has null for its next element. Well, where's B at? Well, its address is stored in A, not anything down here. So really, if I want to remove from this end, I would have to come in at the head end and navigate my way down, keeping track of what the previous nodes are whenever I'm on a current node. So that way when I get here and see the null and know this is last, keep track of that the previous node I saw was B, so I can make these adjustments. Well, that's sort of a big hassle, and plus if this is a long linked list, there's a computational effort to searching it. So really I'd rather do this. So I'm going to remove from the head end, and add to tail end. And by the way, the terms for these, so removals are dequeues. And note there's another data structure called, I think it's pronounced dec, spelled like that. That's not what we're doing. And here we're enqueuing. I don't know why they didn't just say add and remove, but I didn't make it up. All right? So that's what we're going to do. But there's another wrinkle we need to consider. What happens when I'm creating a brand new queue? This one already had 3 nodes in it, and so tail pointed down here, head pointed down here. But when I create a brand new node, or queue, excuse me, which will have this initial node, this will be both the head and the tail. So how do I deal with it? Well, let me copy over what we did for this, add to the tail end, because we're going to look at something. So I'm going to say add to existing to keep track of it. And so we said we had temp malloc, or temp equals malloc, store the data, temp next equals null, because remember we're adding down here. And then we said tail next is equal to temp, and then tail is equal to temp. Right now we're talking about create new. So what do we need to do? Well, we have temp malloc, store the data, temp next equals null, and then what needs to happen? All it left is say this is head and this is also tail. So we'll say head is equal to temp, tail is equal to temp. Now these two steps are really independent of each other, so I can do these in either order. But these two are not. As I described before, if I say tail equals temp first, then this doesn't work right. So this has to be in this order, but these can be in either order. So what's the same? Temp equals malloc, store data, temp next equals null, temp next equals null, tail next equals temp, and head equals temp are different, and then finally tail equals temp and tail equals temp are the same. So how can I choose between the two? Let me put this here. So what we need to do? Well, if I set, when I create the variable and say struct node star head equals null, that's my way of knowing there is no queue. So I can say, after I do these 3 things, right? So do these parts, then ask this question. If head's equal to null, then what we will do? We'll say head is equal to temp, else tail next equals temp. And then regardless of which thing we do, then we finish it up by saying tail equals temp. So that's the process. So now let's write the code to do that. So here I have a structure definition. This would be my data, right? I is equal to 1, I is less than 5, I plus plus. And now here we're going to have a slight wrinkle from before. So before, when I was creating a stack, and I didn't have a tail variable, which I've created here, I didn't have a tail variable when creating my stack, so when I would write the function to allocate the memory, store the data in the memory, and then I would somehow need to say head equals temp, I just returned the temp and assigned it to head here. So I did this. Head equals, in that case we were pushing data, so I had this. But now, as we just saw, I also need to do things with tail. And in the scenario where I have an existing linked list and I'm adding new nodes to my queue, I don't update head, but when I'm creating a brand new queue, I need to update both head and tail, which means I can't do this. I mean, I can do it for one variable, but what do I do about the other one? So instead, I need to be able to update both the head and the tail variables. Tail, regardless of whether or not the linked list already exists, but head in the case of a brand new linked list. So I'm going to do this. We said this is enqueue. But now if I'm not going to return them, that means I need to use a pointer to do it. So I'm going to pass in head as well as tail. So here's an application where I have to use pointers somewhere along the way. So let's write the function to do that. So this would be void enqueue struct node star h struct node star t. I could call this head and it's a different head, and tail would be a different tail, but I'm doing it here so I can discuss it and you know what I'm talking about. Int n. And what needs to happen? Struct node star temp is equal to malloc size of struct node store the data, so that's going to be temp x is equal to n set next to equal null. And remember, we said that now I need to ask a question. So I need to say if my existing head is equal to null, do one thing, otherwise do something else. But how do I know where head is at? And actually these are wrong. I just realized that. These need 2 stars. So I need a pointer to a struct node in both cases. Because that's what I was getting at here, that star h now is an alias for head. So now I'm talking about this spot in memory. If it's equal to null, then star h, or head, is equal to temp, else star t next is equal to temp, and regardless star t is equal to temp. Here I definitely don't need the parentheses. Here I wasn't sure, so it doesn't hurt anything to include them. So by doing these things, I'm assigning the values directly to these variables. So let's see what happens. And let's put this here, so we can see it growing. And actually there's a, well, I'll need this here for a moment. So now if I'm adding things to the tail end, Well, if the first number I store is 1, that should be at the head end. When I store number 2, that's at the tail end. So head is still 1. When I add 3, that's at the new tail end. So head is still 1. So when I print things out, they should be in order. So there's the 1, which would be that way either way. But here's the 2, here's the 3, here's the 4. What I'm getting at is that when I was printing the list, when I did all the adds at the head end, then I print in reverse order. Because each new number is added at the place where I start. So at the end, I would have had 4, 3, 2, 1. All right? So let's see how to remove. Well, dequeuing is basically the same process. Now, one of the things I'm not going to check here, but you really would need to do, is that if we're dequeuing, we would need to check that the queue is not empty. Because if the queue is empty, then we would not want to dequeue. Let's do this. We'll say void dequeue. And so we said removing from the head end. So the process is, and I'm going to do this. I'm going to use pointers again, although here I wouldn't technically have to. I could just return it and do a reassignment. So the process was this. We said struct node star temp is equal to head next. So head is really this. Now we're able to free the head, which here is star H. And now, say the new head is equal to where temp is at. So now remove from the head end, so that's the 1. And actually we could go through and say, as long as the head is not equal to null, we're safe to free. So we could do that if we wanted to. But let's just do another dequeue. Right. And so we can continue. So that's how you construct a queue using a linked list. If you find videos like this helpful, then please hit the subscribe button.